All right, so let's start. So as Shailin mentioned, I'll be talking about how to compute electron phonon scattering rates and perform transport calculations. Uh, we will be running in particular calculation mode setup for the grid setup im sigma to get the scattering rates, trans RTA, that's RTA relaxation time transport, trans mag RTA, that's relaxation time magnetotransport, and then their full Boltzmann version with and without magnetic fields. So if you haven't already, please uh, uh, open up or please download all of the relevant files, including the EPR file from the link that was sent earlier, and also from the GitHub repo for the Perturbo Workshop. We'll be performing the calculations on silicon, so you can download all the relevant files from this hands-on 3. You have this silicon directory. I assume once you do that, I can fire up my version of Docker. To start. Okay. Looks like we are in. I already have a pre-existing version. So currently inside Docker, I've copied all of the relevant files for the silicon directory. And inside we have 2 folders, Perturbo and QE2Pert. If you have the relevant EPR files, please put them inside this directory so that you can later soft link to this directory for all of your calculations. So I'll navigate inside Perturbo. We have all of the calculation modes inside different directories over here. And we'll be starting with the setup calculation. So Pert setup electron. Now let me explain the input files a little bit, even though it was already done in the tutorial yesterday and partly in the hands-on session today. So for the setup calc mode, we have to specify the calc mode equals setup. We have to specify the grid that we want to generate along the 3 crystallographic axis. In this case, we will be using a 40 cubed grid. Additionally, we have these extra parameters, Boltz Emin, Boltz Emax, bandmin, bandmax. And it was also explained in the tutorial yesterday, but it's worthwhile to just take a look at what these mean in the context of the material that we'll be studying, which is silicon. So if you look at this band structure plot for silicon on the left, Boltz Emin and Boltz Emax specify the energy window that covers a significant portion of the conduction band, which will be mainly contributing to transport. Bandmin 5 and bandmax 6 means these are the 2 bands with indices 5 and 6 that we'll be using in our transport calculations. There is this flag, find E Fermi is equal to true. I will explain what that means in a minute. But before that, let me go to the temper file.
Question.
Sure.
So here the energy window, the minimum is 6.4, but as long as it's below CBM, it should be
right. It should be the same. But we also, because you can put your chemical potential anywhere within the gap, we want our chemical potential to lie within the energy window, which is why I've put it a little bit below the band edge. So if you want to put your chemical potential of Fermi level somewhere here, which is the ideal, sorry.
Okay. And also, why do you want to only look at conduction transport?
Oh, we can, I mean, we have done both conduction and valence bands, but for the purposes of this calculation, we'll be just talking about conduction band transport.
Eventually, we should include both bands for experimental comparison.
Well, the gap is actually significantly big. So if you place your chemical potential in the case of silicon, you can see the indirect band gap is roughly about 1 electron volt. So if you put your conduction, if you put your Fermi level somewhere close to the conduction band, it will only excite the electrons in the conduction band, and the whole transport would not matter much. Which is why we can separate the two. If you have a metal or a semi-metal where the band edges are close to each other, that's when both electrons and holes are thermally activated. So even if you just do conduction band, I think that should take care of that should still give you significant physical results. Yeah. Right. So yeah, that was a good point. We'll only be studying the conduction band in this case because the gap is big, and because if you place a Fermi level or chemical potential close to the conduction band edge, the holes can be nearly neglected. So let's go to the temper file. In this case, I'm calling it si.temper. And as explained by Khoa yesterday, it consists of several columns. In this case, we are only showing 3 of them. I'm neglecting the magnetic fields up to the point where we actually need to perform a magnetotransport calculation. So the first column represents the temperature. The second column represents the location of the chemical potential. And the third column represents the carrier concentration. The first line, it explains, well, it tells you how many configurations you're specifying, or you have to specify the number of configurations that you will be specifying in this temper file. Now, let me go back to per.in in a little and talk about this flag find e Fermi is equal to true. As Khoa had explained yesterday, for now it's commented out, but and by default, this flag is set to false. So what this means is that inside the temper files, even though we have 2 different columns for chemical potential and carrier concentration, the setup calculation and the transport calculations and everything else, they will only consider one column. So if the flag e Fermi, find e Fermi is set to false, then by default, we'll be performing our transport calculations by considering the chemical potential and then calculating the carrier concentration from that. And if the flag e Fermi, find e Fermi is set to true, then we'll be using carrier concentration to get the chemical potential. So both of these will not be used simultaneously. Now, this is a simple calculation. Oh, okay. I already have the file, the soft link, but let me just show it real quick. You can create a soft link to wherever you have stored your EPR file. In this case, it's inside QE to Pert. And what else do I need to? Yes, and now I think we can run the calculation. So Perturbo.x, NSI, specify the input file, and the output. Now this was a rather quick calculation. By the way, the commands are also inside GitHub files if you just want to copy them onto your terminal. So this is a rather quick calculation. It generates the number of tetrahedra that fall within the energy window, the number of K points for our 40 cube grid that fall within the energy window, and then the number of irreducible K points, which is significantly smaller as we would have expected. Also note that the energy window here is specified from 6.63 to 6.9. This is because even though we selected our Bolt's E-min to be 6.4, this starts from the edge of the conduction band. So if you want to figure out where your conduction band edge is, this is one of the places you could look for. So,
no.
Yes.
When you set to find Fermi level, do you use the charge neutrality equation?
Sorry.
So if the code is asked to find the chemical potential, if the code calculates chemical potential,
yes,
it is based on the concentration, right?
Yes.
So it uses the charge neutrality equation.
I'm actually not sure how it actually computes, but there is an equation where we have the expression for carrier concentration in terms of
that's charge.
Okay, sorry, that's okay. That's
and in that you have an assumption that the carrier concentration in this is fully ionized, right?
Yes, yes.
Okay.
But we are neglecting ionized impurities inside our calculation. So because this is close to the because the Fermi level is within the gap.
Okay. And if so, this is like we have one EB gap. It's okay to just look at the conduction band. If the material has a very small gap, is your code able to take into account the chemical potential properly? Like the charge neutrality will include both the conduction band and valence band.
It will, but then it
Will.
wouldn't physically make sense to.
Well, for very tiny bandgap material,
Yes, for tiny bandgap material, you can specify your energy window such that includes significant portion of both valence and conduction bands, and you can compute carrier concentrations from the chemical potential. But either it will give you the electron concentration or the hole concentration. It cannot separate the two components.
it cannot.
No,
Really?
I mean it
It
doesn't.
can, for semi-metal material,
Yes.
okay, it cannot.
No. I mean, I don't think there is a way to separate. What you can
Really?
do, what you can do is you can actually specify your band index to be just the conduction band. Place your Fermi level where you want. Calculate the concentration for
Yeah,
electrons.
I understand your procedure, but for semi-metal, it's impossible for you to only consider a conduction band.
Yes, that yes. So
Yeah, a direct semi-metal.
yes, we have.
We need to consider both electrons and holes.
That's right.
Yeah.
So we specify both the conduction and valence bands inside
Okay.
this. Yeah, and the energy window to be close to the Dirac the Dirac point.
Okay.
Anyway, so this calculation generates several output files, doping, SI, prefix.doping, prefix.dos. But all of this, and most importantly, it generates the KPT or the K point files, both in the text format, si underscore tet.kpt and si underscore tet.h5. And all of this information is also contained inside the YAML files. So if we can just go through that real quick, you'll find that it contains information about, well, the basic data, which is already in the EP1 file. Additionally, you have information about the grid points. You have information about the density of states, which is specified here as a function of energy. And there's the density of states. It also specifies the carrier density for each of the configurations, since here we only have one configuration for which the parameters are specified over here. It computes the carrier concentration off of the chemical potential. So now that we are done with the setup calculation, we can move to the next, which is PERT im sigma electron or calc mode im sigma. So if you could go back one directory and navigate to the directory PERT im sigma electron. Let me start. By the way, this calculation computes the imaginary part of the self energy, and you can extract the information about the scattering rates from this from these values. So here is the input file. You have to specify the calc mode equals im sigma. You have to specify the K points for which you want to compute the imaginary parts of the self energy, the temper files, the band indices, which we used in the setup calculation. Then there are several additional parameters. The first one is PHV cutoff, which is the phonon frequency cutoff, which means that we'll be neglecting all of the scattering processes where the phonon frequencies are below this cutoff. The delta smear, as was explained in the lecture yesterday, that represents the smearing value of the Gaussians that we use to estimate the Dirac delta functions. Then there is another flag called sampling, which is the type of Q point sampling that we want for our calculation. In this case, we are choosing uniform sampling. And the number of Q point samples to be 64,000. Now, as I said earlier, we need to specify the K point file where we want to compute these electron phonon scattering rates. In this case, I will copy that file from the PERT setup calculation. So copy si tet.kpt file from there. Additionally, we'll need to create a soft link to the EPR file. And I think we are ready to run the calculation. Now here, because Perturbo is both MPI and OpenMP parallelized, and for the purposes of Docker, we are not using MPI parallelization, but we are still employing OpenMP parallelization. So we need to specify the number of OMP threads, since doing so will actually help speed up the calculation. So you can do that. You can copy this command from GitHub. So export OMP num threads equals 8. Because my PC has a maximum number of 8 cores, I can specify up to 8 threads. If you have a quad core or a dual core PC, you can adjust the number of threads to 4 or 2 accordingly. Now we can run the calculation. Turbo.x. Oh, sorry. I think I made a mistake somewhere in the temper file. Oh yes, also, you need to copy the temper file from the pert setup calculation, as this was not an input already. So you need to copy the TET files and the temper files from the setup calculation, and then I think you can run. So now it starts running the im sigma calculation. This is the output file. Here it mentions that we are running the calculation on 8 processor cores, specifies the parameters such as band min, band max, the number of K points where it will compute the electron phonon scattering rates, and this is the number of Q points that it will use to compute the summation. There is also a progress bar that shows how much or what portion of your calculation has completed, and right now it's up to 30%. So please let me know when your calculations are done, and in the meantime, if you have any questions that I can answer. Yes.
So I tried making a soft link to the EPR file. But when I do it and then I try running the Perturbo.x, like the T per out,
Yeah.
it says that it's missing the file.
Oh, okay.
But then when I hit ls to check
the
file's there, but when I open the file, it's empty. I guess it's that.
Oh, okay. Did you copy the EPR file off of the tutorial link that was sent earlier? Or?
I just downloaded the entire GitHub file.
Oh, okay. Sorry, yeah, I should have been more clear about that, but the EPR.h5 file is in the tutorial link. I can actually share that again in the chat.
Oh, it's not on the GitHub.
Oh, it's not on the GitHub because it's a huge file. It's 2 gigabytes. Sorry, yeah, I should have specified that, but you can find your the link. Let me actually find or you can go inside the Perturbo website, and I believe somewhere here it should specify a link to the box folder. This link was the link to the EPR file was also sent in the chat earlier, but if you click on these box folders, you'll find the example for silicon, example 2 silicon Perturbo, and inside QE to Pert, you'll find the EPR file. So if you could download it and copy it to the QE to Pert inside your, it should be able to detect that file, the soft link.
Thank you.
Sure.
Drew, there's also a question for metals. How do we need to choose the energy window?
Right. So yeah. Okay. So right. So for the case of semi-metals or metals in general, let's talk about Dirac semi-metal for simplicity. You have these conduction and valence bands that touch each other at a single point in the Brillouin zone, right? So what you do is you choose your energy window. That's if you have your chemical potential near the Dirac point, then you choose your energy window such that it covers a sufficient portion of both of these bands.
How do I tell it is sufficient? What parameter?
Well, if
should I look at?
No, if you're, for example, doing 300 Kelvin temperature, then you know just from thermal smearing that only regions with energy window KBT are thermally activated. So if you could choose an energy window that's sufficiently large, we recommend choosing an energy window of 6 kBT both above and below the Fermi level.
Yeah. That's understandable, but is there a way to do convergence test? So I can take a look at what parameter gradually converges. So if I include more energy window, it never changes. Is there a parameter there in the output?
India. You can test, I suppose. So it depends on the. So if you're trying to do
Yeah, because sometimes in metal you have a large DOS and including more window, even though like 3 kVg, it will take a long time, right? So if I want to do a smaller test, I want to make the cost really minimized.
Right.
Yeah.
How would you?
I want to test on the convergence. What parameter should I look at?
I would recommend checking out. So if you are trying to do a transport calculation, I would recommend looking at the M sigma calculation for starters, or well, I would look at the values of the conductivity tensor as a function of the energy window, and if it doesn't change significantly, so I see what you're going. So in the case of metals, you are expected to have sometimes a large density of states, which is why you'd like to choose the smallest energy window possible.
Yes.
And in that case, the way to normally check for convergence would be
Directly look at the variable.
directly look at the right. No, absolutely. But regardless, I think at least a window of 3 kBT, regardless of whether it's a metal or a semiconductor, should be included. Otherwise, you might miss out on important K points that do contribute.
And also on the tutorial, it says it's not a completely converged calculation.
Yes.
In the M signal, where should I set for it to be completely converged?
So as this imaginary part of the self-energy calculation involves a summation over the Q points. And currently I have chosen it to be 64,000. For the case of like completely converged silicon calculations, this sampling is usually much larger. In the case of silicon, uses at least like 500,000 or 1,000,000 Q points to get.
Well, do you have a rule of thumb for how large it should be, or I should also do a convergence test?
Well, I mean, a convergence test is essential for most of these.
So you typically use 100 cube. Is that?
Yes. So if you have 100 cubed Q grid should again ensure. But again, if you have a system with extremely sharp bands, then even 100 cube grid might not be enough. So it's always advisable to check for convergence on both K and Q grids.
And this imaginary part of sigma should also tell me the lifetime. Where can I get that lifetime output?
Well, right. So let's talk about the outputs now, assuming that you have finished the M sigma calculation.
Not yet. Still.
Okay, no worries.
Okay.
In the meantime, I can explain the outputs to you. So there are several files over here. The output files here are si.imsigma. Sorry, let me go back to my GitHub page. So there are several files, si.imsigma, si.imsigma_mode. So the prefix.imsigma should give you the values of the imaginary parts of the self energies. And in order to, you can actually extract them in an easier manner just by looking at the YAML output file, which is si_imsigma.yaml. So again, it contains information about the basic data. And there you have this flag imsigma, number of bands, number of phonon modes, number of K points, and the K point grid itself. Now, here we have the energies of each of these K points. And there are the values of M sigma that corresponds to each particular value of energy. So the relationship between the scattering rates and M sigma is that you can compute the scattering rates by multiplying the imaginary parts of the self energy by 2 and divided by the Planck's constant. So what I would recommend doing is, the inverse, the lifetimes can be calculated simply by taking the inverse of the scattering rates. So if your calculation finishes, I would recommend checking out the Perturbopy website, since it contains extensive information about, I'm putting this link again in the chat so that everyone can see it. Is there a way I can share the link with the attendees?
If you go in the chat, do you have the option to send to everyone?
It says host and panelists, but there's no option for
All right,
everyone.
send it to
Okay.
Isaac, and I think he's able to.
All right. Yeah, Ivan, could you send this?
Yes, I can send the link there. Yeah. Okay.
Thanks.
Yeah, sure. And yeah, for our in-person participants, though, I don't know if everyone is on Zoom, so I think it would be easier just to type that perturbopy.readthedocs.io. No need to type all of the all of the continuation.
Yes. So
it's just
perturbopy.readthedocs.io. So if you could just type this, it directs you to the Perturbopy website that contains a good amount of information on how to post-process some of this data. So on the website, under the post-processing section, there is another section for tutorials. And that gives you an extensive, a detailed, comprehensive explanation on how to perform these post-processing calculations for each of the calc modes. So for the case of Im Sigma, if you could just go to Im Sigma tutorial. First of all, it tells you how to import the Perturbopy package, assuming that you have downloaded, how to import the Perturbopy package, assuming you've already installed it. And yes, also, you can load the YAML file inside this object si_im sigma. And I believe there should also be scripts to print out these different attributes that fall under this object. I also have a plotting script that uses Perturbopy inside the Pert Im Sigma electron folder. So what we do is we essentially load this and then plot the two attributes, bands versus, Im Sigma as a function of the band energies. So if you want to extract, for example, the lifetimes, I believe you can do some additional 1 or 2 lines of code to convert this quantity into your electron phonon lifetimes. The scattering rates are 2 over h bar times the imaginary parts of the self energy, and the lifetime is 1 over that, or the inverse of this.
So I just need to plot 1 over this.
1 over this times the additional constants.
Okay. There is no built-in thing to time the.
Well, yeah, I mean,
okay.
it's one extra step away, but yeah.
Okay.
Yeah. So yes, we can use this plotting script to plot our imaginary parts of the self energies. Notice that you will have this additional si-imsigma.png file that we can open and see that it contains scattering rates. So there you go. These are the values of the imaginary parts of the self energy as a function of the band energies. Okay. So back to the.
So it basically says the near the CBN, the lifetime is longer.
That's what we would expect, yeah, because there are fewer states to scatter into and out of. You would expect larger lifetimes for a smaller density of states. So if we are done with the Im Sigma calculation.
And one more question is, it's not that for each mode, it must have calculated this, but this diagram must have summed over the modes.
Yes, so if you want to plot the mode resolved scattering rates, I believe that information is also inside the YAML file.
Okay.
And the Perturbopy website can also print, Perturbopy can print out this attribute for you. That's mode resolved values of the self energy, if you want to plot them as a function of different modes. So if you're done, I assume everyone's done with this calculation. If then we can move on to the trans port trans RTA, which is the calc mode trans RTA or alternatively trans, and that all the relevant input files should be inside the directory port dash trans dash RTA dash electron. The input file looks similar to the previous input files that you've seen, except that the calc mode is different now. These parameters such as grid sizes, energy windows, the temper files, everything else remains the same as we had in the setup calculation. And additionally, we have this step bolts underscore end step equals 0. What this means is this is the number of steps that we use for the iterative approach. This flag is not really useful for a relaxation time calculation as it's not an iterative calculation. So we can just set it to 0. Now, this calculation mode takes the temper file as inputs. Now notice that you already have a temper file inside this directory, and it's different from the temper files that we have used earlier. Since now I want to plot or compute conductivities at different values of or at different temperatures.
But in principle, different temperatures will shape the Fermi level section.
If you want to, yes, at different.
So in principle, I should redo the chemical potential calculation for every single temperature.
Well, because we are fixing the Fermi level and computing the carrier concentration from.
Physically, you cannot fix the Fermi level.
Yeah, physically, it doesn't make sense for you to do an RTA calculation with fixed Fermi levels. That does not conserve the carrier concentration. But yes, so and also note that you already have an im sigma file inside this directory, as this would need to be generated again. We cannot reuse the one that we did earlier because now we are doing 5 different configurations instead of a single one. So now we can create a soft link to the QE to PERT of the EPR file. And oh yes, also I should specify that this im sigma file is optional for the relaxation time calculation, meaning that if you do provide it, that's great. That will mean the calculation finishes faster, but if you don't provide it, then the code is also capable of computing these scattering rates on the fly. But in this case, we do provide it since we want a easier calculation. So let's rerun. Sorry, I should specify that you also need to copy the tet.h5 file that was generated as part of the setup calculation. So PERT setup electron, copy the si_tet.h5 file to this directory, as it will read the information about the grid from here. Now I think we have all the, yes.
Oh, I'm not sure if this was said in earlier tutorials, but why do we need to make a soft link? What is the purpose of it?
It's just normally sometimes these EPR files are larger. You can copy them, of course, but creating a soft link means that will save you the trouble of copying a huge file. So, sure.
If it does not have imaginary sigma in this folder, will it redo the calculation by itself?
Yes. Okay. So if you do not provide the im sigma file as the input, it will redo the calculation. But if you have already done it, it's much cheaper.
So for example, this current image sigma is different from what has been calculated.
Yes, because previously we were only specifying one temperature configuration. For this calculation, we are doing 5 different temperatures. So this im sigma file contains.
This one is larger.
This one is larger, and it contains 5 different configurations.
I see.
Yeah.
Oh, that's why you put a new file.
Yes, that's why it's a new file. So let's run the calculation. As you can see, this will be a rather quick calculation. It also prints out the progress as it's doing different configurations here. It's done in less than 5 seconds. There are several output files generated, but again, as said previously, all of this information is contained inside the YAML files. So it will print out these transport properties, including the conductivities, mobilities, even the Seebeck coefficient at that point. So there you go. Prints out the conductivity tensor, different components, the mobilities, and also the thermal transport coefficients. So again, a Perturbopy website, let me go back to that real quick. It also contains information about how to post-process transport data, and the directory. So if you can refer to this this page to see how you can load different transport attributes and print them out, or do some post processing, including plotting them. In this case, we have different temperatures, so we can plot them as a function of temperatures. I'm not plotting it for the relaxation time right now, as I want to compare this calculation to the full Boltzmann equation. So I can show you the script on how to plot them. So is everyone done with this calculation? Then, yeah, sure.
So we calculate the electrical conductivity, and like, so we also found this thermal conductivity.
Yeah.
So does it just conversion using with transfer that you got the electrical conductivity?
Oh, no, it calculates the thermal conductivity within the core using this parameter. So in the lecture yesterday, as I mentioned, there's a separate variable for thermal conductivity that we can. So yeah, it computes it from it doesn't convert the electrical to the thermal. Yeah. So
Sorry, so you mean the thermal conductivity does not necessarily follow Whitman transfer because it's computed? I mean, RTA issue for the Whitman transfer.
I assume that's implicit in the Boltzmann equation when we solve for the thermal conductivity.
Okay.
Wiedemann transfer. Yeah.
But after iteration is not necessarily the case.
Well, we can always check for it.
Yeah.
So, yes. If everyone's done with this calculation, then we can move on to the next step, or the next calc mode, which is per trans mag RTA electron. It's the same as trans RTA, except that you change the calc modes here. And because it's a relaxation time calculation that involves a magnetic field, it's an iterative process. So that's why you have to specify the number of maximum steps that you will be using. I set that to 20 over here. Again, please note that the temper file is not the same as before. And now it contains fixed temperatures and chemical potentials, but I'm varying the magnetic field. So these last three columns represent the X, Y, and Z values of magnetic fields in Tesla. And because we have a different temper file, we also have a different im sigma. So if you're doing it from scratch, you will have to rerun the im sigma calculation with this configuration. In this case, you can just use the im sigma file that's provided inside that folder. So as usual, we can copy the TET file that reads the grid information. So SI-TET.h5 from the setup calculation. We can, and also now let's create a soft link to the EPR file. And now I think we can run this calculation. And again, because we already had the im sigma file, it's a quick calculation, and therefore it does not compute the scattering rates again. But if you do not provide the same sigma file, it will in fact recompute the scattering rates and takes longer. So this was the calc mode trans RTA with and without magnetic fields. Now let's move on to the calc mode trans ITA, where it solves the full Boltzmann equation. Trans ITA represents the calc mode where it computes the electrical conductivity without any magnetic fields. As usual, it contains the information about the temper file, the information about the temperatures and Fermi levels inside this prefix.temper file. Note that now this is a regular B is equal to 0 or 0 magnetic field transport calculation. So we are doing different temperatures and fixed chemical potential. We also need to copy the grid information from the default setup calculation. So let's do that. si_tet.h5. And then finally, we can create a soft link to the EPR file. Now, note that we have seen the case where we actually provide an ImSigma file. But for the iterative transport calculation, you can provide the ImSigma file and it will use it as a starting point. But even if you do, regardless of whether you provide the ImSigma input file or you don't, it will still compute the scattering rates because now we have this extra backscattering term where we need to compute the individual scattering processes. So I'm not providing the ImSigma file here, and you will see that when we run the calculation, it will actually compute it on the fly. Let's first export or specify the total number of threads that we want for this calculation, and then we start running it. Now, this may take a little bit of time on your machine. So in the meantime, if there are any questions, I'd be happy to answer them.
Can I talk about the node in Transact ITA? It's like slightly below on the left.
This one?
There, on the left on the tutorial with me.
Oh, yes. Okay.
Yeah, there is a node slightly behind, slightly below.
Okay. This
No, it's like go down.
go down.
Yeah, this node.
This one.
Yeah.
Oh, yes. Okay. That's actually a good point. I should specify that. So while this calculation is running, I should specify that this flag is called load_scatter._EPH. And by default, it's set to false. I've commented it out over here. But what you can do is if you already have done a transport calculation with the same grid parameters, same energy window, same everything, then it stores the information about this electron phonon matrix in a temp file. And for if you want to try out other different configurations, such as different temperatures or different magnetic fields, then you don't need to rerun this electron phonon calculation. What it can do is it can simply read the information about this electron phonon matrix from the pre-existing calculation. And in order for that to happen, you'll have to uncomment this flag and specify load_scatter_EPH equals true.
Is RTA considered a pre-existing calculation for ITA?
No, because RTA does not store these information about electron phonon matrix in the temp files, especially if you provide ImSigma, because it just computes it sums over the Q point scattering rate. So it does not give you Q resolved values of scattering rate. So only for ITA calculations will you actually need to, is this flag helpful? I mean, for an RTA calculation, if you don't specify the ImSigma file, then it's worth considering this load_scatter_EPH flag, but yes.
Okay, so it's also not useful to use it for magnetic field. It's also not transferable.
Oh, it's transferable to magnetic fields. So if it's a
Okay.
magnetic ITA calculation, it's transferable because for that
Okay.
you will still need the individual scattering rates for each KQ pair. So that's what we'll do. In fact, after this calc mode, we'll be doing the magnetic field calculation. And since I'm already computing it here, we'll just be reusing the electron phonon data from this temp file. So you can see how this flag plays out in that context. Seems I'm running slightly behind on time, so I'll have to skip some material, but hopefully.
On this, there also a convergence issue.
With
Yes.
convergence issue
So
with
previously we have the N sample.
Yes, in this case, oh yes, actually, I don't know why. Sorry, I should mention. I should have started with the input file first before running the calculation, but I can show you that what the input file looks like, and you can see that inside the folder. It's slightly different from the RTA input file. Well, it's the same as RTA input file, but for the iterative calculation, there is another parameter called volts queued in. So something like this, where you specify the phone on grid that will be used for convergence. So instead of phone on random samples, the ITA calculation uses the phone on grid for convergence. I did not specify these three flags over here. So so by default, it assumes the same Q grid as the K grid. But if you want to specify a Q grid, a different Q grid, and it has to be commensurate with this one, then you can specify that using these three flags, volts underscore Q grid.
Okay.
Yes.
And previously used random sample. The n samples equals something.
Yes. So previously we were doing random samples, but for the iterative calculation, because you need to compute the backscattering processes, it's better done when you have a Q grid on the first Wheelon zone that's commensurate with your K grid. Okay, so on my end, the transport calculation is done. It prints out these files, conductivity, the transport distribution function that I was talking about yesterday. All of this information, again, it's contained inside the YAML file. So now we can actually plot the conductivity tensor for this system as a function of temperatures, as we were doing different sets of temperatures and fixing other parameters. There is a plotting script inside this directory, and it loads both the YAML files for the relaxation time calculation that we did earlier and the iterative calculation. It loads the YAML files, it stores the attributes, the temperature attributes inside these two variables. The mobilities here, as mobility is a 9-component tensor, we have to specify which component we are plotting. So here I'm doing the 0, 0 component, which converts to the XX or the X values of the mobility. And now we plot these two. So it's stored inside this image si trans.png, which looks like this. So this is for the case of silicon. Mobilities as a function of temperature for different for RTA versus ITA. And as we would have expected, they are different because there is an extra backscattering term. Same plot on this GitHub over here. Yeah, I'm definitely running out of time. So I will exclude this calculation pH mode exclude ranges, but I can just briefly go over it. What you can basically do is specify another parameter or another flag called pH underscore mode underscore exclude ranges. And this will set the electron phonon matrices for these particular phonon modes to 0. So if you're trying to compute phonon mode resolved transport properties, this is a very useful flag. You can run this calculation in the same manner as you ran your iterative calculation. The only difference will be that you have to specify the number of modes that you are excluding over here. For the case of...
I have a question about this.
Sure.
You exclude these two bands, and you have done an iterative solution.
Yes.
And will it be additive if you just include these two bands? I bet not.
No, because the conductivity goes as relaxation time, right? So it's 1 over the scattering rates. So definitely it's not additive.
Well, okay, if it's 1 over, will it still be additive if I just take inverse?
For iterative, no, because then you also have this extra backscattering one. So yeah, no, definitely. That's a good point. So yeah, here I'm excluding 2 modes. You can actually check out on you can try.
How do you interpret this band specifically? And I know iterative you cannot really add them up, because after iteration you cannot really sum them to get the full iterative result.
It gives you a more physical intuition on what bands are contributing to your final transport, right? So you can plot band resolved or mode resolved quantity, phone on mode resolved quantities, not band resolved, and you can see which one's the closest to the iterative. So even though it's not additive, you can still find out in a manner of speaking what portion of your transport coefficient is contributed to by different modes. And it's definitely not intuitive. That's why we have this flag that helps you exclude these modes. Okay, 4 minutes. Real quick, I will do a trans mag ITA calculation, same as trans ITA, except that you will have to specify the calc mode. Everything else stays the same. Note that I've uncommented out this flag, load scatter EPH equals true. So now what we can do is we can copy the temp file that was generated in the trans ITA calculation to this folder. So it will simply read the electron phonon matrix from there. Let's take a quick look at the SI.temper file. It again is at fixed temperatures, but now we are varying the magnetic fields. And now create a soft link. Copy the tet.h5 file from the setup calculation. And I think we are ready to run the calculation. So we can do turbo.x. And now you see that it simply skips the step where it computes the electron phonon matrix because it just reads it from the temp file that we provided. So yes, it's doing the magnetic transport, the magnetic ITA transport for 5 different configurations, 5 different magnetic fields. And it's done. This was a quick calculation because we already had the electron phonon matrix. If we didn't, then it would have taken the same time as it did for the previous one. There is another plotting script that I have over here. Now we are loading the RTA and the ITA calculations with the magnetic fields. So this was the previous calculation that we did earlier. I'm loading these objects. And now we want to plot the Hall components or the XY components as a function of magnetic fields. So store the magnetic field attributes inside these variables. Store the Hall conductivities, which is the XY component. Notice that I've changed 0, 0 to 0, 1 over here. And then we simply plot them. So let's take a look at that and see how the plot looks like. SI trans mag. Now you can see that it contains, well, it's Hall conductivity as a function of magnetic fields for RT and ITA calculations. And as we would have expected, it's different. So with that, I'd like to conclude my talk. And I have 2 more minutes if there are any questions.
Well, in this transport calculation, you say you can pre-save some file.
Yes.
And that is the electron phonon matrix element. But previously, we also got it from earlier calculations. Like, why do you only save this file for transport calculation, not in earlier calculations?
In earlier, as in at the im sigma calculations?
Oh, yeah.
In the im sigma, we are using a different, we are using a random Q sample versus for the iterative, we are using a finite Q grid. So it doesn't make sense to store the KQ pairs for a random Q sample, because it's going to be different every time.
Okay. So why do we use random sampling in sigma?
Because this was just an example. You can use the Q grid in the im sigma calculation.
There is also Q grid.
There is an option where you can specify the Q grid. If I had time, I can explain that to you after my talk. But you can specify the Q grid inside the im sigma calculation. But for polar systems and everything, if you have an important sampling, it's obviously much easier to converge.
And in im sigma, if I specify the grid, will you also give me this matrix file?
No.
So only saved in transport.
Yes.
Okay.
Yeah. It's done slightly differently from the transport calculation. I can explain that in more detail. Yeah.
Thank you.
All right. Thank you.